So we can always check it graphically. We can always solve it graphically if we need that. If we need to do it algebraically, then we have to change our process a little bit. So the first thing that we do is we find the values of the variable which make the expression within the absolute value symbol equal to 0. Just looking at the absolute value symbols. This is like when we're trying to solve our piecewise function, where we know that this is where it's going to change shape. When the absolute value equals 0, then it would change directions or reflect, because that's where it would drop below the x-axis if that was the function. We're going to divide the domain into smaller subdomains using the different values found in step 1. Once again, we're going to say when it's less than an intercept or when it's bigger than an intercept, the shape would change. We write the absolute value expression in piecewise form so that we know what solutions should fit into that range. And we solve the resulting equation in each subdomain. Which means that, like with our piecewise function, we're going to have the positive version, we're going to have the negative version. And we solve for if the absolute value was the positive version of it, or if the absolute value was the negative version of it. And that's going to give us different possible values for x. Last but not least, because of the way that it reflects, it can wind up with extraneous roots, or roots that don't actually show up, just like in many of the units that we've talked about so far. So we always need to confirm that the solution is valid within that range. So let's take a look at it. Alan started to solve the equation, the absolute value of 2x plus 3 is equal to 8. Using the steps on the previous page, complete Alan's work and check the solution with a graphical solution. So he found that if he took that absolute value of 2x plus 3 and said it was equal to 0, then x would equal negative 3 over 2. There's where the x-intercept would occur. There's when it changes, which means that I have two possible subdomains, when it is smaller than the intercept or when it's greater than or equal to the intercept. Now, we also know because of the piecewise function that the absolute value of 2x plus 3 would be the original form, 2x plus 3, if x is greater than or equal to that negative 3 over 2. And it would be the negative version, negative of 2x plus 3, if x was less than 3 over 2. And that's how we decided what's going to fit into each part. When it was in the greater than section, he used the positive version. When it was in the less than section, he used the negative version. And then he's just solving it. If negative of 2x plus 3 is equal to 8, then negative 2x minus 3 would equal 8. Negative 2x is going to, when I move the 3 over, equal 11, and x would equal negative 11 over 2. And then I just double check. Is the solution I got here, negative 11 over 2, smaller than negative 3 over 2? It absolutely is. So there's one of my solutions. When I take the positive version, where it should be greater than negative 3 over 2, then 2x plus 3 is equal to 8. 2x is equal to 5, and x is equal to 5 over 2. And 5 over 2 is, in fact, bigger than negative 3 over 2. And that one works. Is the solution in the subdomain? Yes, in both cases. So x is equal to negative 11 over 2, or 5 over 2. And we already know that from doing it graphically on the previous page. If I am algebraically solving, or in this case, Haley is algebraically solving example 1a, which we did graphically, algebraically in this case, then I'm going to start by taking a look at that absolute value and stating if 3 plus x was equal to 0, x would equal negative 3. So negative 3 is going to be where that x-intercept happens, and my two possibilities are that x is less than negative 3 or x is greater than or equal to negative 3. Based on my piecewise, I know that when x is less than negative 3, it's going to be the negative version. Negative of 3 plus x is equal to 2x plus 1. When it is greater than negative 3, it's going to be the positive version. Positive 3 plus x is equal to 2x plus 1. And I'm going to solve both of these. If negative 3 minus x is equal to 2x plus 1, then I'm going to subtract 1 from each side to get negative 4. I'm going to add x to both sides to get 3x. And then when I divide both sides by 3, negative 4 over 3 is equal to x. Is negative 4 over 3 less than negative 3? No. So I'm going to reject that solution. Doesn't fit in the domain. When I try the positive version, then I'm going to subtract 1 from each side to get 2. I'm going to subtract x from each side to get x. And I know that if x is equal to 2, 2 is in fact greater than negative 3. It fits into the subdomain. And my final solution is that x is equal to 2, which once again matches with our solution from example 1a. Another way that we can solve this is by actually just using the piecewise function. So if I'm using piecewise, then I could take my point, take the absolute value, and know that the dividing line is at 3. And I can say that the absolute value of 3 plus x would equal the positive version, 3 plus x, if x is greater than or equal to negative 3, or negative 3 plus x if x is less than negative 3. I'm going to set each of the expressions equal to 2x plus 1, and I'm going to verify the possibilities. If I take the positive version, 3 plus x is equal to 2x plus 1. 2 is equal to x. So if x is equal to 2, then I can sub it back into my original form. The absolute value of 3 plus 2 is equal to 2 times 2 plus 1. This would be the absolute value of 5 is equal to 4 plus 1. The absolute value of 5 is 5. 4 plus 1 is 5. And we know that that works. We take the negative possibility. Negative of 3 plus x is equal to 2x plus 1. Negative 3 minus x is equal to 2x plus 1. Negative 4 is equal to 3x, and x is equal to negative 4 over 3. When I put it back in to verify it, then if I said that 3 plus, sorry, absolute value of 3 plus negative 4 over 3 is equal to 2 times negative 4 over 3 plus 1. Then this is going to give me the absolute value of, when I take away the negative 4 over 3 from the 3, I'm left with positive 5 over 3. And this is going to give me negative 8 over 3 when I multiply it by 2. And that 1 is going to become 3 over 3. Absolute value of 5 over 3 is 5 over 3. And negative 8 over 3 plus 3 over 3 is negative 5 over 3. And those are not equal to each other. And I'm going to reject that solution. Now, for example 5, it wants us to take the absolute value of x squared minus 9 and the value of 7. I'm going to graph out the left side. It's going to look something like this. With those x-intercepts occurring at negative 3 and positive 3. I'm going to have the right side, where y is equal to 7. And I'm going to find, and I'm going to find 4 points where they cross. The two inside points are going to be rounded to positive or negative 1.41. And the two outside points are going to be positive or negative 4. If I use that same example or same method that I did in the last case to solve for the possibilities, then I'm going to take the positive version of my absolute value and say that I have x squared minus 9 is equal to 7, which means that x squared is going to equal 16 when moved to the other side, and x would equal the positive or negative square root of 16, which is the same as positive or negative 4. I'll take the negative version, and I'm going to say that negative of x squared minus 9 is equal to 7. Negative x squared plus 9 is equal to 7. Subtract 9 from each side, and negative x squared is going to equal negative 2. I'm going to divide both sides by negative 1. X squared is equal to positive 2. And then x would equal the positive or negative square root of 2, which can be rounded to the positive or negative 1.41. Now, we know that we want to keep the exact value, so we're going to just leave it as positive or negative square root of 2, even though through the graph it's going to round it. And then when I verify all 4 of those, they all work. All right, go ahead and get some practice.